So that's the biggest loss I mentioned. Like, oh, Molly, my sister did gymnastics for like 15 days ago. Yeah. Okay, so it's just like my stuff on the yellow. Yeah, very good things. Yeah, I was wondering, because I have the whole people, like, even though I can follow it, and then like, I know, yes, like, yeah. I mean, just, I mean, it's really on. Yeah, but yeah. But that's like, oh, it's so fun, and plus the format. Yeah. About the picture friends. Video. Yeah. Oh, you don't understand. Never sound not. Everywhere. Yeah. Great. Just like. Really?
Okay, I think what I want to do is I do want to check your homework page 7 through 9, but today's homework will just be the classwork as well. So I figured we'll just work through page 12. And at the end of class, I'll just walk around and check page 7 through 12 and give you 2 days worth of homework grade. Right. So I think we can get through everything we need to get through in class today before I check your homework. Okay, so I think we left off with part A. So page 9. So page 9, we talked about how we are still going through extreme value theorem to find our absolute max, absolute min. But what's different is we have to kind of go through this adapted formula to find our positions at these endpoints. So if they give you an integral like this, then you just plug in and you just find whatever that returns you, and that's going to be the location. But if they don't give you a formula and they only give you a starting point, then you want to use this final equals initial plus displacement, where we have an anchor point, we have our graph, and then we're using both to figure out where this object is going to end up. I think we got through part A, but let me just recap here on page 9. We first created our F prime sign line. And then because we have our derivative graph here, any x-intercept and endpoints are the critical points that we're ultimately considering. And we're putting them into the formula here. We're starting at f of -1, and then we're figuring out how much progress this object has made in terms of displacement. And we got -2, 3, 0, and 8. And absolute max is 8, absolute min is -2, since we're just comparing these y values. Okay, part B says write the equation of the line tangent to the graph when x equals 5. So we're going to be using this formula again to just find the location of the graph. So f of 5 is equal to f of -1 plus the integral from -1 to 5 of f prime. So we're just trying to figure out where the order pair is. So f of -1 is what's given to us, which is 3, plus whatever gap is between -1 to 5 and between -1 to 5. We're having to add this triangle and this triangle, but not this piece here, since we're only going up to 5. So if we know that this triangle on the right, this big triangle here on the right is 8, I can subtract 1 from this little piece to get that remainder portion, which is now 7. So that's how I got 7 minus 3 is 4, or 7, yeah, 7 minus 3 here, which is 4. And then so therefore 3 plus 4 equals 7. So we have our order pair for our f of 5. And the next up, f prime of 5, we need to find the slope at that point. And because this is the f prime graph, f prime of 5 is just the order pair. So f prime of 5 is equal to 2. So we have our order pair, we have our slope, point slope form. This is just linear approximation. And then we build our tangent line equation. And then plug in the decimal with linear approximation, plug in that 5.1 into our tangent line. Okay. Any questions here? Okay, page 10. This is similar to the process that you did on the solving differential equation test. So it's the same stem as the previous page. But here part C says we have g of x equals the integral from 3 to x of f prime. Find g of 3, g prime of 3, and g double prime of 3. So g of 3 is going to be involving the area. G prime is going to be involving the order pair, and g double prime will be involving the slope. So let's see if we can fill that out. So we know that g of x is the integral from 3 to x of f prime. I'm just going to build out all my formulas, and then we can plug in 3 in for all the variations that we need to build. So we know g of x is just whatever is given to us, right? And g prime, therefore, must be the derivative of this. And if this is sitting at a level above f prime, we know derivative is going to bring this down, was going to kind of strip this away and make it go down to f prime. But I can just kind of show, going through second theorem here, that I'm ultimately trying to find the derivative of this mess. And anytime we see a pairing of 2 opposing operations, we know they can cancel each other out. The upper bound gets inserted for t. So therefore, g prime is just f of x. After all this is, after the dust settles, and we can cancel this out. So we know g prime is just f, which means that if I want to build g double prime, I'm just making this go down 1 derivative level. So I'll make this go down 1 derivative level. F will turn into what? What's 1 derivative below f? F prime. So they're kind of at a staggered relationship here. G is the area or displacement of f prime. G prime is the f graph. Sorry, the f. My bad. Hold on. F. I'm sorry. So when these cancel out, I need to hold on to this, whatever this function is. And this function was already at f prime. So g prime is f prime. And so therefore g double prime is f double prime. So again, normally it's staggered, but this is already at f prime. So when we take out the integral, we should need to hold on to that f prime, and then therefore g double prime is f double prime. Okay, so let's see if we can find all the pieces that we need to find. So G of 3. Okay. Again, we're on page 10 if you were coming in late. G of 3 is just the integral from 3 to 3. We just want to place wherever the x has the definition telling us to put in, so 3 to 3. Anytime our bounds are the same, we know we haven't moved at all, so our area is just 0. G prime of 3 is just f prime of 3. F prime of 3 is just the order pair. So the order pair, that's up at a y value of 2. And then G double prime of 3 is f double prime of 3. And f double prime of 3 is just asking for, this is f prime, so f double prime is just the slope. And then the slope of this line is just going to be 2, right? We're going to go up 2 over 1. You can close the door. Thanks. So G of 3 is 0. G prime of 3, the area, order pair, slope. Typically, when you see a limit problem on the AP exam, typically how it's going to work is, let's just review what we do. When we do limit problem, we always do direct substitution first. And if we get a real number, then great. That's our final answer. If we get 0 over 0, that gives us the green light to do L'Hopital's rule. So there's going to be at least multiple L'Hopital's rule on the AP exam, and you can expect to see one on Friday's quiz as well. Yes. So I went up 2 over 1 to get that to be the slope of 2. Problem 3. Yeah, the scale may be a little different here. It looks like it's a little bit thinner here, or it's a little bit more, but we just have to kind of follow whatever that this graph has for us. So the first thing we do is we plug in 2, and College Board is a little nitpicky when it comes to L'Hopital's rule. So typically, especially if it's free response, use arrows. Don't use equal sign. I'm not going to care in terms of, if you use equal sign on the quiz or the test, I'm not going to take off any points. But just let you know, College Board, they don't, technically it's not equivalent to, whenever you use equal sign on the FRQ, the graders are instructed to look at both sides of the equal sign to see if they're actually equal. But sometimes we don't use equal signs that way, right? We use equal signs sometimes to indicate, oh, this is my next step. I'm not committing to the fact that they're the same. But for College Board, they're going to treat equal sign. They have to look at both sides and see if they're equal. So to get around it, just to tell the grader, hey, I'm not committing to these both are the same. I'm just telling you what the next step is. So the safer play is use arrows so that you don't get points taken off because they're trying to compare both sides of the equal sign. Okay, so first thing we do is we plug in 2 because that's direct substitution, right? We always want to do direct substitution because we don't know what's going on. This is our way of evaluating. And if this gets us a real number, then we can stop. That's our limit. If it gives us 10 over 0, then we say limit doesn't exist. But if we get 0 over 0, that means it's in a determinate form. The limit does exist. We just haven't found it yet. We just have to go a little further. So f prime of 2, we look at our graph. This is the f prime graph. So f prime of 2 is 0. So we get 0 up top. And the denominator is e to the 2 minus 2, which is e to the 0. E to the 0 is 1. 1 minus 1 is 0. So this gives us the green light to do L'Hopital's rule. Okay, so we can't stop here and say the limit doesn't exist. The limit does exist. It's just there happens to be a hole here, but the graph is still going to move towards the same y value. So L'Hopital's rule says we can take the derivative of the numerator and the denominator separately. So what's the derivative of f prime? That's what? F double prime, okay. And then e to the x minus 2, remember the rule for e to the u is e to the u times u prime. So e to the x minus 2 just remains e to the x minus 2 times 1, right? Because x minus 2's derivative is 1. And the minus 1 just goes to 0. So as soon as you find the derivative of the numerator and denominator, you can reevaluate, and the hope is that this will lead us down to a real number, and then hopefully we can stop and say that's our answer. So we plug into f double prime of 2 over e to the 2 minus 2. So f double prime of 2, now we're asking for the slope of the f prime graph, which we found before as 2 up 2 over 1. That's the slope of this line segment. So then we're left with 2 over e to the 0 is 1. Now we have a real number, and that's our answer. So careful that you're taking this step first before you jump into the derivative, because I see some students, they say, oh, this is L'Hopital's rule, and they start finding the derivative without first confirming that we have met the conditions for L'Hopital's rule. The reason that we got to do the step is sometimes the problem may just lead you down the right answer. If this evaluation gave us like 3 over 4, then we don't go through L'Hopital's rule because we already have a real solution. We only move into L'Hopital's rule if we get a 0 over 0. Okay, page 11. Okay, a sand pit is being filled with sand whose height at any time given by a differentiable function h of t. H prime is a differentiable function representing the rate at which the height of the sand pit grows. So at 0 minutes, the sand pit is growing at a rate of 1 inch per minute. Then at 1 minute, the sand pit is growing at a faster rate, 2 inches per minute, then 5 inches per minute, then 7, then 10. So the rate at which that pit is growing is accumulating at a faster rate. It is known that H prime is increasing on its entire domain. So H prime is always going to be increasing, even though we don't see what's between each of these times. Values of H prime are given. The height of the sand pile is 40 inches at 9 minutes. So they gave us an anchor point, but these are all rates. Okay. So part A says estimate H double prime of 2. We know that if we're given H prime and we're asked about H double prime, that's derivative, but we can't do derivative if we're only given a table of values. So what's the algebra version of derivative? We can find the what? What can we do? take order pairs and find what? Slope, yeah. So slope is the algebra version of, because we can't do derivative, we don't have enough to build a function, but we can find slope. And it says estimate, so we just picked points around 2. The closer we are to our source, then the more accurate we're going to be able to get. So h double prime of 2 is just the change in the rate of h prime, or the change in h prime divided by the change in time. Squiggly to indicate that this is just an approximation. We don't know the exact h double prime of 2. We're just estimating based off of nearby values. So 5 minus 2 over 3 minus 1. So the change in h prime divided by the change in time. 3 over 2. What's our new unit of measure going to be? Or will it just stay inches per minute? Or will it go up to inches? Or inches per minute squared? So this is already in terms of inches per minute. We're dividing by time, so it's inches per minute per minute. So inches per minute squared. It says, explain the meaning in the context of this problem. So this inches per minute, we don't want to say acceleration. We don't want to say rate of a rate. We want to say that the rate of increase, or the rate of the sandpit height, is increasing, right? We want to be able to use that. If you see a second derivative, typically we want to be able to say rate is increasing or rate is decreasing, to use those words there. So we can say the rate of sandpit height is increasing at 3/2 inches per minute squared at t equals 2 minutes. Right, we see the rate is increasing, right? From 1 to 2, 2 to 5, 5 to 7, 7 to 10. So the rate is increasing. Part B, use Wright-Riemann sum with subinterval to approximate the integral from 0 to 12 of h prime. So Wright-Riemann sums using the subinterval. What that means is we want to then make every subinterval a width. So from 0 to 1, from 1 to 3, from 3 to 9, from 9 to 12. So width is 1, width is 2, width is 6, and width is 3. Width times height for each of them. It says Wright-Riemann sum, so what that means is for the height, we're going to choose the one on the right for each subinterval. So for the first subinterval, we'll choose a height of 2. For the second subinterval, we'll choose a height of 5. Third subinterval, height of 7. And last subinterval, height of 10. And then these numbers here are your width for each of your rectangles. And this adds up to be 84. Now we're accumulating these rates over a time period. H prime is inches per minute. What do you think the integral is going to do to it? Will it stay inches per minute? Will it go to inches per minute squared, or is it something else? Just what? Just inches, yeah. So this tells us over the course of these 12 minutes, after all the accumulation has occurred, the sand pit is going to grow 84 inches in this 12-minute period. Part D, evaluate the integral from 0 to 9 of h double prime. So one way to interpret this is we can find the area under the h double prime graph. But if you look, we don't have an h double prime graph in front of us. So maybe we can turn this into something else. Maybe we can get this into a different form. Maybe we can evaluate this, right? If I take the antiderivative of h double prime, what is that going to turn into? H prime, right? And we just plug in our upper and lower bound. This is basically a application of first theorem. We make the integral rise through a level to a level above, and then we plug in our upper and lower bounds. So h prime of 9 minus h prime of 0. Right? We're just making this go through first theorem. And h prime of 9 is from the table, which is 7. H prime of 0 is also from the table, which is 1, and we just get 6. And then our units of measure is going to change into inches per minute. So what this tells us is that over the course of the 9 minutes, the rate has increased 6 inches per minute. Right? It was only at 1 inch per minute, and by the time it gets to the 9th minute, it would have increased up to 7 inches per minute. So the rate has increased by this amount over this 9-minute period. Yeah. Page 12. Same stem. Write equation of a line tangent to the graph at t equals 9. So we're just trying to build our tangent line equation. So let's find our order pair. Let's find our slope, point slope form. And then we can plug in the 10. Normally it's a decimal value that we plug in, but in this case, they're asking for an approximation at an integer value. Okay. So let's find our order pair first. H of 9 is equal to we can't pull this from the table, right? Because this is all H prime, but they do give us something that we can use. They say that the height of the sand pile is 40 inches at 9 minutes. So there's our order pair. H prime of 9. We have that from the table, right? H prime of 9 is just going to be 7. Point slope form. Normally, point slope form is y minus y sub 1 equals m times x minus x sub 1. But we can just adapt it using the variables that we have, right? So we can say h minus h sub 1 is equal to m times t minus t sub 1. So h minus 40 equals the slope, which is 7, and then t minus 9. All right, just like with point slope form, we're replacing these three pieces. M, x sub 1, y sub 1. Same thing here. We'll replace m, t sub 1, h sub 1. Okay, solve for h. we have our tangent line equation, and now we just have to do our linear approximation. So plug 10 in for t. So we want to know whether is 47, we know 47 is just an approximation, but is it an under approximation or over approximation? And the way that we can tell is it says that it's known that H prime is always increasing on this entire domain. So if H prime is always increasing, then H prime is going to end up looking something like this. So it's going to have that concave up graph look to it. If H prime is increasing, that means my second derivative is positive, which means that it's concave up. And any approximation that I do on a concave up graph is always going to sit below the curve. Meanwhile, if something is concave down, then any approximation is going to be an over approximation because any point on that line is going to sit above the curve. But here, concave up, my approximation, my linear approximation to that tangent is always going to be under approximation. So we can say, since H prime of 10, sorry, H double prime of 10 is greater than 0, our graph is concave up. So therefore, linear approximation value is going to be an under approximation. Part F, explain why there must be a value between 9 and 12 such that H prime of C is equal to 8. Well, we have an H prime of C graph here, right? Between 9 and 12, can we guarantee that our H prime is going to hit 8 somewhere between? We can, right? It's a continuous function. We're initially at 7 inches per minute, then it rises to 10 inches per minute. It's got to pass 8 inches per minute somewhere between. So this is a IVT. So intermediate value theorem is a little bit easier because we can kind of just visualize it a little bit easier. It's like, oh, okay, I see a point below, I see a point above, it's connected. I got to hit every point in between. So we can say since H prime is continuous, so that's the only condition that's needed for intermediate value theorem. And since H prime of 9 is equal to 7, and 7 is less than 8, and 8 is less than 10, which is coming from H prime of 12. Therefore, there must exist a value C on the interval from 9 to 12, where H prime of C is equal to 8. So IVT, I think, is easy to spot, but it's a little bit cumbersome to write it out, but it's basically saying, okay, I have a point that's below my target. I have a point above my target. I know that every point is going to be connected between the two endpoints. So I've got to reach my target somewhere in between. Part G, explain why there must be a value such that H double prime of C is equal to 3/4. Now we don't have H double prime of C because we only have H prime, but we know H double prime is the slope or the derivative level of what we can see. So that's usually involving mean value theorem. So there's sometimes they like to pair these two together because they're both kind of related. But if something that you're looking for is at the level that it's given to you, then it's usually IVT. But if something that you're looking for is at a level that is a derivative below what's given to you, then that's going to be mean value theorem. So mean value theorem is a little bit harder to visualize because we don't see those numbers in front of us. We just have to trust that the slope is going to show up. So if I can show that the slope between these two endpoints is 3/4, then there must be a place where the slope is going to be exactly 3/4 somewhere along that H prime graph. Okay. So we have to state our conditions for mean value theorem. So since H prime is continuous, specify the endpoints and differentiable, parentheses, and let's find the endpoints. So we're going to do H prime of 12 minus H prime of 0 over 12 minus 0, and see if this actually ends up being 3/4. It should. If it does, then we can guarantee that if my average slope is 3/4, I've got to be able to hit that exact slope of 3/4. So H prime of 12, we look at our table, we get 10. H prime of 0 is 1. 10 over 12, sorry, 9 over 12 is 3/4. So if between 0 and 12, I'm getting a slope of 3/4, there must be a place between 0 and 12 where the exact curve, the exact steepness of that curve is also matching that 3/4. Okay, let's move on to page 13. Let's just maybe just do A and B together and then we'll be done. Okay, so let's do another 10 minutes and then we can stop. Okay, so page 13. You have a couple of information given to you. You have a table of values, you have a graph, you have a function that's defined. So see if you can try part A. Find the slope of the line tangent to f at x equals pi. So find the slope means you're going to plug pi into the derivative. So find the derivative of f of x using your derivative rules, and then plug pi into the derivative to get your slope. Okay, so think about what's the derivative for cosine of u, and think about what's the derivative for e to the u. Okay, cosine of u becomes negative sine of u times u prime. E to the u becomes e to the u times u prime. Okay, plug pi in for x. Sine of 2 pi is 0, so that wipes out. Sine of pi is also 0, but e to the 0 is 1. Cosine of pi is negative 1, so negative 1 times 1 will give me negative 1. Okay, let k be the function defined by k of x equals h of f of x. Find k prime of pi. And you guys look at this and recognize what rule do we have to do to get to the derivative? Same rule, yeah. So outsize times insize derivative. So spend a minute, see if you can build out your derivative using chain rule. We can plug pi in. Make sure that you remember your steps for chain rule. It's not just h prime times f prime. It's outsize derivative times insize derivative. Okay, so build it piece by piece. This is going to be tough to do in one step, but we can do f of pi, right? Get that number, then do h prime of that number, and then we can pull them from different sources. So f of pi, we're going to have to plug pi in for the f function to get that value. So f of pi. Step to the side here and find that value. So f of pi just means I'm going to plug pi into the original here. So cosine of 2 pi plus e to the sine pi. Cosine 2 pi is 1. E to the sine of pi is 0. E to the 0 is 1. 1 plus 1 is 2. So 2 is going to be your f of pi. Okay, so now we have that information. We can update our derivative. So this is pulling from h, right? H prime of 2. So that's asking for the slope of the h graph at 2. The slope of the h graph at 2 is here. We have to find the slope of this line segment. So I can go from end to end and just count, rise over run, down 1 over 3, negative 1/3. The slope of this line segment is negative 1/3. So we have negative 1/3. And then f prime of pi, I think we can pull that from what we've gathered from part A. F prime of pi is negative 1. So finally, negative 1/3 times negative 1 is just 1/3. Okay, we'll finish page 13 tomorrow, but if we can just flip through page 7 through 12 for me. And I can just check you off for both days of classwork homework.
Yeah.
I guys can come get your phones.
Yeah, we should back. Yeah, I didn't fit.
Yeah. I went in.
What if I'll clear it for you, but that's if I have there's stuff. Yeah.
Yeah.